Yeah.
Why don't you
Okay,
pass it
KJ,
on?
just hold this here, please, would you? No, it's okay.
Can you put something underneath that?
Yeah. Okay.
Or maybe buy a new one.
I'm not paying anything.
Don't you ask the AC to pay for
Oh,
it?
that'll take ages.
You'll get one?
You should be finished by the time I get it.
Useless.
A new cable.
Seriously?
Possibly.
You can order it from eBay?
Yeah, but then I have to pay for it. You think they'd let me use the credit card? You don't trust me with the credit card. Right, fields. And we are on, what was it now? Where is it?
Induction.
Induction. There it is. Right. Alright, so let's have a look at some examples now. Come on. Come on. You can do it. There we go. Okay, so we blah blah blah, and then we had this, and then we had this, then we had lenses, and then we had that, Faraday, the generator, and then we had this, and AC, and the hand, and final hint,
And then slap.
and then slap. Right, okay, so write this one down now. This is our first example.
Isolated cover.
Huh?
Isolated cover.
Yeah. Okay. Okay. So can I do this one now? Okay. Yes?
Yep.
Okay. So you have a copper wire wrapped around the metal pipe, which is 35, 30 by 5, 100 times, and a 1.5 magnet running through it. Okay, so what you got here is you got your copper, you got your pipe, and it's 30 centimeters long, and it's 5 centimeters, 5 centimeters in radius, was it, or diameter?
Wide diameter.
So it's 5 centimeters altogether. And then you have your copper wire that's wrapped around it, and this goes around 100 times. So if I take a magnet here, north-south, and run it through this pipe, the change in magnetic field will cause a current to appear in the copper wire. What would be the direction of the current? In other words, here, should I draw an up arrow or a down arrow?
Down arrow.
For what reason?
It's coming towards the
Yeah, what's the name of this law? Lenz's law says that the current will go this way. So while the magnet is moving through the pipe, there's a current, okay? Now I won't bother with the minus sign because the minus, we already know it's heading towards us, whatever, we don't need to know about that. So it's n change in flux over the time. Now the n we do know, it's 100. The flux, we don't know yet, but the time we do know. What's the time?
3 seconds.
3 seconds. Now, we have to work out the change in the flux, which is the change in BA. Now, the A, the area, is not changing. Because, I mean, these are all circles. That's not something that's changing. What is the thing that's changing? The magnetic field is the thing that's changing. So it's A delta B, which is pi r squared delta B. What's the or? It is 0.025 squared delta B, which equals 1.96 times 10 to the minus 3 delta B. Now here's the question, the delta B. How is the magnetic flux density changing? How does it change? In what way is it changing? How can we say it's changing?
It goes from 0 to 1.5.
That's it. At one moment at the time we don't have a magnetic field, and then the magnet enters the pipe and we have a 1.5 magnetic field. So the change is we're going from a 0 to a 1.5. And over how much time is this change taking place? 3 seconds. Oh, we already put the 3 in. So the delta B, if you want to write it like this, is 1.5 minus 0. So the answer I get is 2.95 millivolts.
Do we know it goes from 1.5 to 0?
Well, there's no field at the start when the magnet's outside. And then when the magnet's inside, then you have the field. And the question said it was a 1.5 magnet, Tesla magnet. Now it's not 2.95 constant, you know, that's just a 2.95 average, because of course at the beginning the voltage is 0, then it will peak upwards and then go downwards here. So it's, you know, it's just an average. There's about 2.95 millivolts while the magnet is moving through the copper, through the pipe.
So now we should just put spot in the question?
But this is it, this is it. The question was what's the voltage, that's it there. Okay, can we go to the next one? Yeah, okay. No, no, no. Chill out. Chill out. Right. So write this one down.
Plane. Have you seen the news?
No. What? About Google?
No.
No. About what then?
Quick.
No. Don't care about that.
It was about Ireland.
I might care a little then. The good news?
No.
I don't care about it.
Where's Santa Claus?
That should say the climbing speed is 600.
Is that maybe Tesla or mega Tesla?
What does your heart tell you?
It could be mega.
No, no. What does your heart tell you? Give me an answer. Milli or mega?
Really?
You are correct.
Is that Wingsman or Wingspan?
Wingspan.
Okay.
You asked me if that was wingman. No, there's no wingman in this question, alright? The plane is going solo.
Maybe Wingspan there to help Santa.
Wingspan's there to help Santa. Santa and his wingman. Got it?
Yep.
Yeah? Okay, so let's draw this. So I'll try and draw it in 3 dimensions if I can. So that's the surface of the Earth, and then what happens here is you have your plane, and it goes, that's the runway, and of course it goes down the runway and it takes off. So there's a magnetic field. Since it's heading to Santa Claus at the North Pole, we'll say it's pointing towards the North Pole. So do you remember that Santa lives at the north, but the magnet in the Earth is actually upside down. So we go from north to south, so the magnetic field is going this way. Now, what do you mean?
Where's the south?
Huh? The plane is like here, heading that way.
Okay.
Yeah? So this is the magnetic field heading this way. Now, this problem is like the generator problem. The plane is made of metal. Metal is a conductor. Okay? And so when a conductor moves in a magnetic field, or equally when a magnetic field moves around a conductor, we get a current. Which direction will the current be? Well, we'll have to use our right-hand rule here. So, notice, please, that we don't care about we don't care about this component, because this movement is in the direction of the magnetic field. It only matters the movement that takes place perpendicular to the magnetic field. So any movement perpendicular will have a current. So if this is my conductor, and this is my magnet here, so well, there's the magnet there, and there's north and there's south. I mean, this doesn't do anything. It's only motion which is perpendicular to the field that we care about. So that means here it's only the vertical speed of the plane that we care about, not the horizontal speed. It does nothing for the current, okay? So, what's this finger for?
Thrust field.
The motion. So, the plane is taken off, so it's going up. What's this one? The field. So, if I'm sitting in the plane, so this is the plane here, the motion is upwards, and the field is going straight ahead, heading to Santa. So, which way is the current?
Left.
To the left. So in my picture, what's going to happen is there'll start to be a current running across the plane. In fact, if you could stick a voltmeter around the tips of the plane, you could measure it. Now you might say, well, are you sure that the forward motion doesn't matter? And you said, yes, but think about this. The motion must be perpendicular to the field. If the motion and the field were in the same direction, you would have this. It just doesn't work. They have to be perpendicular. So we only care about the upward motion of the plane. What is the formula here to get the current? Well, it's E, the voltage, equals... Now, is there any loops here? No. So, and do I care about the minus? I don't, because I know which way the current is going. It's going to the west. So it's just the change in the flux over the time. The speed is 600 meters per second vertically, the climbing speed. Okay. So because this is continuous motion, it'll be convenient if we look at this on a per second, but what? No, you're not listening. I just said there's no end because there's no loops. Nobody came along and put a wire around the wings. It's just one wing. Right? You're hurting me. Here, right here. It hurts. Okay. What was I saying? Oh, yes. So, because this is continuous motion, we should deal with this on a per second basis. So that means the time per second, so the delta t is... No, this is not working. You're disconnected, you're not listening to me, you're not even looking at me. We are looking at this on a per second basis. So what is the delta t? 1, because it's per second. Now what is what is the flux? It is BA. Now what is the thing that is changing, the B or the A? Tis not, because the Earth is not changing its magnetic field. It's constant everywhere. True?
Yeah.
So what is the thing that's changing?
The
The A. So the B is the same, and it's the A that is changing. The B is 0.07 millitesla. Now think before you speak. Think about what exactly does it mean to say the area is changing. Because the plane is not changing shape, the Earth is not changing shape. So what do I mean by the change in area here? No, there wasn't enough thinking time. That was not enough thinking time.
motion.
Yeah, but what is the area which is changing?
Area of the motion,
He's not far away. So you keep your laughs to yourself. He's done better so far than you.
By the plane
changes,
move.
Yes. The area here, don't care. People needed more time to think. The delta A is the area that the plane sweeps out. So as the plane climbs, the wings are sweeping out an area. Per second how much height has been added to the plane? 600, because its speed is 600 meters per second. And what is the length of the plane? Well, it says it in the question, it was 68.5 meters. So per second, what is happening is that the plane sweeps out an area of 600 by 68.5. So this is a noticeable 0.288 volts, or if you want, 288 millivolts. And you could definitely measure that. So it means that if there was a millivoltmeter in the wings of the plane, this would be one way that the plane could know or detect its motion vertically, because you see, the other thing is, this only is induced while the plane is moving upwards, but as soon as the plane reaches its maximum height, there's no more upward motion, so then the voltage drops from the wings. So this is only taking place while there is vertical motion, because the motion needs to be perpendicular to the field. If the plane was just flying straight and the motion is parallel to the field, there's no voltage then. Okay? And likewise, when the plane is landing, what I think would happen is you get a voltage, but this time it will be going to the east. Whereas in my picture, from using the right hand rule, the voltage is going from the right to the left, the east to the west of the wings. Okay, so when the plane lands at the North Pole, the voltage will change the current will change direction. Okay.
What if the plane was made of plastic? Would it still be correct?
Oh my god.
Is a plastic a conductor?
Will you conduct it?
Yes, because remember the name of the lesson, conductors in a magnetic field. It's not called insulators in a magnetic field or plastics in a magnetic field.
So is there like magnet field in plastic? Or are they conductors?
No magnetic field in plastic. In fact, plastics block magnetic fields. Yeah, no. So you can block a field or interrupt a magnetic field with plastic. You could definitely block an electric field with plastic, and I think well, no, actually, magnetic field wouldn't really be affected by a plastic, but an electric field can be blocked by plastic. Yeah, but there is no magnetic field there. Magnetic fields only appear when a charge moves. So there's not really any free electrons in a plastic, so you couldn't get a magnetic field around it.
And I think that plastic like can't block the electricity, isn't it?
Yes, electric fields and electricity, but I don't think magnetic fields. Okay, so this one here, like I said, that voltage is something you could definitely measure. It's not made up. Like if you had inside the wings a millivoltmeter, it would definitely pick up that voltage as the plane is taken off. So this is this is a real thing. Why might you care about that? Well, do you really want a voltage running through something that has hundreds of gallons of fuel in it? Do you know what I mean? Like, there's a current running through the wingtips and there's a fuel tank. Maybe you want to design your plane so that when currents are induced, it won't cause a circuit to explode in the fuel tank and then the plane crashes. Okay? So, this is definitely a real thing, important for some people's lives. Okay? If you're going to do engineering. Right, let me see. Now, what I'd like to do,
Oh.
now what I'm thinking is I want you to try these now, and then I would like to do them now. And then let me just check how many topics we have left for this section. Right, so we have transformers, Optimus Prime, Coulomb's law, Newton's law, and Kepler's laws. 1, 2, 3, 4. Okay, so we have 4 more topics in this section to do.
How many was we
This
need?
is the last section.
No, there's one more section after this.
Yeah, and then this is the last section.
After this? Yeah. Yeah.
Let's see how many topics are there.
No, that'll ruin the surprise.
No more section?
No. We still have another section to do. Next week we don't have class. Do we usually have class on Thursday? Yeah, of course. This is Thursday. So we'll miss this class next week.
Why?
It's a holiday on Thursday, and then the following week we'll miss the Friday. But we don't have physical on Friday. So we'll have 3 classes next week, and then 5 the following. That's 8. Yeah. So my plan is to get these 4 topics finished before your Easter break. Then when you come back after Easter, we'll do the last section and then into revision. Okay. So I would like you to try these questions now. Yeah, I think they should only take you 10 minutes because they're like the examples I did. Then I'll do them, and if there's time at the end, we can do a little bit of an exam question, okay? So can you just take a snap of this on your phone? It'll be easier for you to see since some of you need glasses. 2 of you, actually. That's a calculator, KJ. Come on. You haven't reached rock bottom yet. You know what a phone is. Have you got it?
I don't think so.
How long are we going to do for the revision?
Huh?
How long will it take for the revision?
Oh, I don't know. Let me see now. This is March, isn't it? We come back in April. I'd say we should get 4 weeks of revision.
Which is the whole material.
We'll try and do everything.
And is there any revision for math?
Definitely.
We'll get some revision in for maths as well.
Some.
Maybe, we will. Maybe not a full 4 weeks. Maybe more like, I don't know, 3 weeks or something.
Yeah.
But we'll get revision in too, because you guys need it, if I'm honest. Oh, I have 2 answers, sorry. So can you try these now, please? I'll give you, there's 5 questions there, it should take you about 10 minutes to do, and then I'll do them. But I need to close this. Where's your phone? Where's your room?
Down.
Downstairs?
Yeah.
Do you want to go grab your phone? Or do you just want to sit beside someone?
No.
You sit there? Okay. Everyone has their picture I can go to? Okay.